Listen to these two notes. The first is played by a piano, and the second is played by a cello, but they're the same notes. So what causes us to distinguish the difference? The answer lies in mathematics. Let's look at middle C, the note that the piano and cello just played. It has a frequency of 130 Hz, meaning there are 130 wave cycles every second. Let's model only one of the waves. This is called the fundamental, and it's the main note that we hear. It sounds a bit bland, right? That's because there aren't any other frequencies. You see, even though we only hear one specific note, there are many other notes being played in the background, and those notes are called the harmonics, and they are multiples of the fundamental. Let's keep going with the middle C. It vibrates at 130 Hz, but it also vibrates at a frequency of 2 times 130, which equals 260 Hz. This is called the second harmonic. And it also vibrates 3 times faster at 390 Hz. This is the third harmonic. It goes on to infinite harmonics. So you might ask, how does the middle C actually vibrate? The fundamental, the third harmonic, the 100th harmonic? The answer is all of them. Let's combine the fundamental and the second harmonic. You can see the outline of the fundamental, and there's also the faster wavelength of the second harmonic. Let's combine the fundamental, second, and third harmonic. It might be hard to tell, but all three frequencies are there. This is what it might look like combining all the harmonics. Then this is an accurate representation of the middle C. Let's listen to this. It's easy to tell that a note is being added because we can compare it with the previous note. However, if I just play this note, you can never tell that there's infinite frequencies and harmonics in there. That's because our ear only takes the lowest and loudest note, the fundamental, and ignores all the harmonics. However, the harmonics does help us distinguish different instruments and voices. This is a spectrum graph for middle C on the piano, and the second harmonic at 260 Hz is louder than the fundamental. However, the same note on the violin, the second harmonic is lower than the fundamental. And all the other harmonics are different too. Finally, going back to the math, the length of the fundamental wave could be marked as 1. So the second harmonic has a wavelength of 1/2, and so on. This creates a harmonic sequence of 1 over n. Another interesting fact is that the sum of the harmonic sequence, also called the harmonic series, is infinitely large. Here's the proof. The top equation is less than the bottom equation. So if the top sum goes to infinity, the bottom sum also has to go to infinity. There's a famous brick stacking problem describing stacking bricks on the side of a table. There's a way for the bricks to never fall over. The secret is that you stack them in length of the harmonic sequence times 1/2. So the overhang is the sum of the harmonic sequence times 1/2. So technically the overhang can be infinity. This means you can continue stacking blocks forever and the Tower of Pisa could look like this. Math can be found anywhere, so I challenge you to find it.